Hello, good morning, good evening, good afternoon, good day, everybody, wherever you might be. It is my great pleasure to welcome my colleague from Göttingen, RALF MEYER, and he will tell us everything and more about C-star algebras generated by Groupoid Correspondences. RALF, the Zoom is yours. Take it away.
Thanks, Giotto, for this invitation to speak in this international seminar. I want to tell you about a rather conceptual work of mine. I have been thinking about this for a couple of years. I've been a bit slow in publishing things because I was kind of sitting on things and trying to make them even better. And part of this was done by one of my doctoral students. I should write down his names in the very beginning. Suniman Albandik wrote his thesis about the construction of C-star algebras from these Groupoid correspondences already a few years ago. I will speak a bit about his thesis. It's available online. And I think one more preprint should come out tomorrow, I think, which is a bit more. And another preprint was published earlier this year together with Celso Antunes, Joanna Coe, and me, which is about C-star algebras generated by a single Groupoid correspondence, you might say. There's more stuff about this, and so I don't have enough time to tell you everything, but I might give you some overview of what this is about.
Okay.
And the goal of this would be to unify various constructions of C-star algebras. And then, of course, the point of unifying these constructions would be to have, well, if you have one approach to a large class of C-star algebras, then you might also have tools that work for all of them.
Mm-hmm.
And maybe you could, well, a possible question to start this would be the question, what is a dynamical system? So the question could be asked then, well, if you think of dynamical systems, maybe the most obvious thing would be you have a topological space, maybe even compact Hausdorff, and then you might have a homeomorphism of that space. But people are also interested in non-invertible dynamics, so they might think about local homeomorphisms as well. But the C-star algebras actually prefer something like graphs and topological graphs. So this definition of a dynamical system should include a graph. And well, of course, the dynamical system for a C-star algebra is a way of constructing a C-star algebra. Like if you have a group action on a space, then, well, you can define a cross-product C-star algebra for this group action. And similarly for a graph, you can define a C-star algebra, the graph C-star algebra. And this should be in some sense one construction. Now graphs and group actions on spaces don't look particularly connected. And well, to see a link between them, you might want to generalize both things further. So if you think about graphs, this is an important, or graph C-star algebras are an important class of C-star algebras, but more recently, people have generalized graphs quite a bit. If you think about generalizations of graph C-star algebras, maybe the first one is just add a topology. So there was something like topological graphs. Something else people did was higher ranked graphs. And well, you could also do topological higher rank graphs. I'm not quite certain this is very popular, but I suppose it wouldn't be a surprise if someone came up with a definition. It's pretty obvious what you should do to define them. Something a bit differently people also looked at was self-similar groups. And the concept of dynamical system that I want to develop will contain the self-similarity of a group as a kind of endomorphism of a group. If you have seen self-similar groups, you might not think that this is particularly close to a graph, but there is actually a way of bringing these closer together. They are self-similar graphs. So this was developed by Excellent Pardo, and it contains graph C-star algebras and the C-star algebras of self-similar groups as kind of the motivating special cases. And well, if you have self-similar graphs, higher rank graphs, topological graphs, of course you can combine all these extensions and look at higher rank self-similar graphs. This was done by Dilian Yang, I think, and I'm not sure anybody has done topological higher rank self-similar graphs, but of course one can do that. And if you did that, then you would probably get what I call a groupoid correspondence. Or if you did it right, let's say, you might say that this is a self-similar topological graph. Well, at least if you define the right-hand side correctly, I would say that the groupoid correspondences would give you a good definition of that. And well, there is still the higher rank missing in higher rank. Well, if you think about the higher rank graph, you have kind of several graphs which are linked together in a certain way. And the way they are linked, I would encode this by a diagram of groupoid correspondences. And these diagrams would certainly contain higher rank. Well, self-similar topological graphs. So that's kind of the scope of these groupoid correspondences. And in all these cases, you can define a C-star algebra from them. In fact, there is something which is a bit different in spirit. Maybe it gets a different color. If you have followed the notion of graph C-star algebras, you might have come across other things which have this, which also have a graph in the name. Like I think there's ultra graphs, labeled graphs, separated graphs, and maybe there's more. Ultra graphs are not so interesting. They're just special cases of topological graphs. So they are interesting in some, well, but they don't add anything new to this list of concepts here. The separated graphs are actually a bit different. A separated graph is a generalization where you actually have two different C-star algebras. One of them is a groupoid C-star algebra or an inverse semigroup C-star algebra, and the other one probably is not. And the separated graphs, I think, would also be a special case of these diagrams of groupoid correspondences. At least some of the prototypical examples would fit into this scheme. So it's a pretty general class of constructions. And of course, if it's so general, then there must be some results which are only true in special cases. And for instance, results for a single groupoid correspondence or for diagrams of a certain shape. But before I go to that, maybe let's now after this motivation, start talking about, well, what is a groupoid correspondence after all? And then how do you attach C-star algebras to them? Unless there's any questions, of course, this would certainly be a good time to discuss any questions you might have at this point.
I have a question.
Of course.
If you construct this graph from this self-similar group, is this construction related to Cayley graph, or is it a completely different idea?
It is quite a different idea. There is no link between Cayley graphs of groups and these self-similar graphs. So a self-similar graph is something more general than a self-similar group. And a self-similar group is a group with some extra structure, which I would call a self-similarity or a groupoid correspondence from the group to itself. And well, I suppose I won't say more about this right now because it's, well, I should get a bit more technical to talk about this properly, but it has nothing to do with Cayley graphs, no. Okay, so what's a groupoid correspondence? I suppose some people here should have come across the term correspondence. So usually a correspondence is defined, for instance, in algebraic geometry, but also in things like bivariant K-theory. There is this geometric picture for it by Conan Skandalis, which certainly Paul Baum would know. I'm not sure he is with us today. So a correspondence would be a diagram, which is a bit like this. You have two spaces, and then you have another space which maps to both of them. And that's what you might call a correspondence. And this kind of correspondence occurs if you look at groupoid correspondences between spaces. Of course, you can view spaces as groupoids, and then the groupoid correspondences will be like this. That's the reason for the name. But the definition is just also inspired by the notion of Morita equivalence of groupoids. So groupoids are special cases of categories. And for categories, the usual notion of isomorphism isn't very useful. You prefer to look at equivalence of categories. And the C-star algebras describe this usually by having a space with two commuting actions and various conditions. So, and that's also the groupoid correspondence is. So if you have groupoids G and H, and maybe I should right away say that when I say groupoid, I mean étale groupoids. Étale means that the range and source maps are local homeomorphisms. By the way, I'm not sure I should explain what a groupoid is. Of course, I can do that if someone wants me to do that, but I would only do if requested. Étale groupoids are the kind of objects between these groupoid correspondences are generalized maps. And a groupoid correspondence would be a space X on which I have groupoid actions. G is acting on the left and H is acting on the right. And I suppose I should remind you what a groupoid action is. So for a groupoid action, let's say for this left action, there's two pieces of data. There is the so-called anchor map, which goes from X to the object space of the groupoid G, which I write as G0. And I just call it R like range map. And then there is a multiplication map, which is defined on a fiber product. So the fiber product is over the space G0 and is using this anchor map R and the source map of the groupoid. And I just write it as sending a pair Gx to G times X. So this anchor map tells me which arrows in the groupoid can act on some element of X. And so therefore there is this fiber product here. And that's the only difference to the familiar group actions. So a discrete group would be a special case of an entire groupoid where you have only one object. In that case, G0 is a single point. So this fiber product is just a product. And you get a group action in the usual classical sense. For a groupoid action, well, you define it only on this fiber product. And then you ask conditions that are familiar from group actions, like if you have the unit arrow on an object R of X and you multiply with X, you should just do nothing, you get X back. And then there should be some associativity. If you have composable groupoid arrows G1, G2, and an X you can compose with those, then you have this condition. So that's a left action. I hope you can guess now what a right action looks like. And for commuting actions, well, you want a relation which says something like G times X times H is G times X times H. And for this to make sense, you also need something about the anchor maps of the left and right action. Maybe I should mention another notational thing. The anchor map for the right action, I always denote by S, like source. So I use the same letter source and range for the source and range maps in my groupoids, but also for these anchor maps in a groupoid action. And my fiber products tend to be over these maps S and R. Okay, so if you ever learned when two groupoids are Morita equivalent, you will use the same data, and then there are certain conditions. I'm not sure who knows these conditions. Maybe let's get a bit interactive. I haven't heard a question or a comment for some time. Anybody knows what you ask for such actions to give a groupoid equivalence? There's a bunch of conditions, and a subset of those will define a groupoid correspondence. Okay, I hope the audience is still listening.
Yeah, I'm thinking, I remember that Morita equivalence of groupoids, it was discussed some ages ago by Zakrzewski, and this is how I know about it. But of course, I don't remember the technicalities. So definitely that the concept of Morita equivalence of groupoids is something nice and important. I know about it, but I also remember that this is quite complicated. There's a question here in the chat. An HS bibundle? Question mark.
Yes, I should probably try to open the chat. And bibundle.
HS bibundle.
Hilsum, HS might stand for Hilsum scandalis. Okay. That's probably what you had in mind. And that's something else. So that's getting interesting because there's important fine print. When you define groupoid correspondences, you choose a set of conditions. Hilsum and scandalis also chose a set of conditions, which is a different subset of the conditions for a Morita equivalence. So what they are doing isn't what I'm doing. But I think it's probably getting too technical for this talk to discuss the differences, the nuances between these different definitions. So maybe let me talk about the conditions that I want. Okay, so there's two conditions for me. The first condition is that the right action has a nice property. So the right action gives me a map from this to X. And I want to take another copy of X and look at the map which sends XH to the pair, let's say X times H and X. If you ever defined when an action of a groupoid or a group is proper, you will also have looked at this map. It doesn't matter how you permute these two factors, X times X. I'm not even sure which convention I normally use, X first or X times H first. And I want that this map is a homeomorphism onto its image.
Yeah, it's also very important for defining principal actions, right?
Yes. That's where it comes from.
Yeah.
In fact, this would be a, well, depending on how we define principal bundles, it could be the definition of a principal bundle. It could be exactly that. The image is always the fiber product over the orbit space of this action. Well, I think I probably want to impose two conditions today. So the second condition would be that the orbit space is Hausdorff. And for those who know more about this stuff, 1 and 2 are equivalent to the action being free and proper. Okay, so I ask for those conditions, and then there's one more, namely the anchor map of this right action is also a local homeomorphism. So you might say I'm looking only at étale groupoid correspondences. Okay, and maybe I should briefly talk about Morita equivalence and how it differs from this. For the Morita equivalence, you would ask a bit more. You would also ask that the orbit space for this right action is homeomorphic to the object space G0. So this map R from X to G0 induces a map on the orbit space, which is supposed to be a homeomorphism. And then you just turn around left and right, so there's kind of symmetric conditions. A Morita equivalence, this is an equivalence-like relation, so everything you ask for the right action, you also ask for the left action. And that's the definition of a Morita equivalence. So in my definition, I don't ask that this X mod H is something specific, and I don't impose any conditions on the left action. Okay, so that's my definition of a groupoid correspondence. And now you might wonder why this definition.
I'm sorry, I'm a bit confused. Could you say again what you mean by symmetric?
Yes. So Morita equivalence is a kind of symmetric concept. So here in my definition, I ask for this right action to be free and proper. I don't ask this for the left action. For a Morita equivalence, you also ask it for the left.
Okay, okay. So in that sense, okay. Yeah, thank you.
And then there is, of course, two maps, X mod H going to G0 and X mod G going to H0, and both are asked to be homeomorphisms.
Okay, thanks.
Okay, so why do I make this specific definition? And the main reason why I chose this specific definition is that the construction of groupoid C-star algebras kind of can be extended to map a groupoid correspondence to a C-star correspondence. I could just write it C-star X. I probably should briefly remind you what a C-star correspondence is, but that requires another page. So let A and B be C-star algebras. An A-B correspondence is a right Hilbert B module with a non-degenerate left action of A. Well, and I ask for conditions like if I multiply A times something in my C-star correspondence and take an inner product, this is the B and the inner product, then that should satisfy this formula. So that's the concept of correspondence between C-star algebras I have in mind. And a groupoid correspondence in some sense lifts this to groupoids. So when you pass from groupoids to C-star algebras by taking groupoid C-star algebras, then the C-star correspondences I defined, the groupoid correspondences I defined give me C-star correspondences. If you ever studied Morita equivalence of groupoids as a C-star algebraists, you might know also that a Morita equivalence between two groupoids this induces a Morita or a Morita refill equivalence between their C-star algebras. And a Morita equivalence is, well, is a bit like a C-star correspondence, but more symmetric. So you also have a left inner product, not just a right one. And then there is some conditions, which I don't have to talk about here. So a C-star correspondence is part of the data of a Morita equivalence of C-star algebras. And similarly, on the groupoid side, a groupoid correspondence is something like a Morita equivalence of groupoids, but you don't ask all the conditions. And well, so this result I've just mentioned about Morita equivalence goes back to Mouli, Jean Reynaud, and Williams. And what they do is they take this Morita equivalence, so a space with two commuting actions and several conditions.
Ralph, you appear to be frozen.
Mm-hmm. Okay, so I'm back after some technical difficulties. the last thing you probably understood from what I told you was about Morley-Renault-Williams constructing a Hilbert bimodule from a Morita equivalence of groupoids. So if you have groupoids G and H, and they are Morita equivalent, then from this you can get a Morita equivalence between their groupoid C-star algebras. And now maybe the short story might be that if X is a groupoid correspondence instead, then the same construction still gives a C-star G, C-star H correspondence. I'm not sure how much I should go into the technical details here. Those who have never seen the example, well, the case for Morita equivalence might not learn much from me writing down these formulas. And those who have seen them, well, for them also it's probably not such a big surprise. Maybe I just leave it at this rather, this kind of statement saying that if you do the same things with fewer assumptions, you get something similar, but with fewer properties. And I chose the definition of a groupoid correspondence exactly so that this happens. So maybe let me just point out a few of the things you have to do here. So, and let me point out that everything I'm saying works for non-Hausdorff groupoids. So G and H could be non-Hausdorff étale groupoids, and the space X could also be non-Hausdorff. But for the purpose of this talk, I don't discuss this. In the Hausdorff case, I get my groupoid C-star algebras, and I also get C-star X by just completing the continuous function with compact support on X. I take that and I define some convolutions with functions on G and on H, on the left and on the right, to make this into a bimodule. And then I define an inner product with values in CCH. And then you have to do some work to show that this can be completed to a Hilbert C-star module. This is in particular positivity of the inner product is an issue. And then you have to show that the left action extends to the completion, all this kind of stuff. And well, I won't tell you how to do this, but in some sense, it's just looking into the old papers and doing it again. Okay, so the message to take home is that the somewhat curious conditions I impose for a groupoid correspondence, well, they were actually chosen to make this argument work. For instance, if you would take instead these Hilsum-Skandalis morphisms, they do not give C-star correspondences, unfortunately, so they are something else, and this construction wouldn't work for them. And instead of going more into the general theory, I might just give you some examples now to see what my groupoid correspondences really are. So let's look at example 1. Example 1 would be Well, the most interesting thing might be endomorphisms. And let's first take a space. Then, what is a groupoid correspondence? So I have here this space and I have another space X. I have anchor maps which go to this space, the range and the source map. And for a space, the action is just the anchor map. That's all there is. And R is just a continuous map. And S is a local homeomorphism. That was an assumption I imposed. This condition of a free and proper action is also empty in this case. And if you look into Katsura's paper about where he defined topological graphs, I think I should probably write this again. Katsura. That's exactly what he calls a topological graph. So here, X would be the edges and G would be the vertices of the graph. So I think of a point in X as an edge from its source to its range. And you ask for this source map to be a local homeomorphism in order to define an inner product on the functions on X. The inner product is just summing over the source fibers of this map. And this only works if S is a local homeomorphism. Otherwise, you would need some kind of a measure on the source fibers to integrate. That's called the topological quiver. And, well, Tom Ford, maybe it was Mooley and Tom Ford who did this. They studied the kind of topological quiver C-star algebras. But this turns out to be much more difficult when you replace spaces by groupoids. So at the moment, I have never looked into this more carefully. So I stay in the world of étale things where this source map is a local homeomorphism and then the inner product is easy enough to produce. Okay, and of course, Katsura used these topological graphs to define C-star algebras. And the topological graph C-star algebra
I understand that there is some asymmetry built in, right? Because
yes.
R is only continuous, whereas S must be a local homeomorphism. So that's on purpose.
Yes, that's on purpose.
Sorry, may I have also a question?
Sure.
So is this does this notion somehow leads to some notion of morphism in some appropriate category?
Yes, it does, but it's a bi-category. That's better. So the groupoid correspondences can be composed, but the composition is only associative up to isomorphism of correspondences. And it's actually important to not identify isomorphic correspondences, but keep them different but isomorphic. So you add two arrows between arrows to make this into a bi-category. I'll come to this when I talk about diagrams of groupoid correspondences. There, this bi-category structure becomes important. But let's first look at a single correspondence, because then you already get everything which is not higher rank. So remember my introduction, I talked about graphs, self-similar groups, all this stuff. And the higher rank graphs and the higher rank self-similar graphs and things like this would actually involve this bi-category structure. But without higher rank, you don't need it.
Okay, thank you. And just a quick question, if you could please remind me, what is the difference between bi-category and two-category?
In a two-category, the composition of arrows is strictly associative.
I see.
You can leave out parentheses and you get the same map. In a bi-category, you don't ask this. Instead, you ask for two arrows that identify them, and they have to satisfy some coherence conditions.
Mm-hmm. So this associativity is up to isomorphism.
Yes.
Okay.
It's a bit like with monoidal categories, if you know those, like tensor products are, or even products of sets are not really associative, only up to obvious isomorphisms or bijections for sets. And these obvious bijections satisfy some conditions that allow you to work with them as if they weren't there, but well, actually they are there, you can't avoid them.
Mm-hmm. I see, thank you.
Mm-hmm. Okay, so that was kind of an outlook towards things to come when you look at more than one groupoid correspondence. But for the time being, I look at one example. I have here my topological graph, which I've now interpreted as a groupoid correspondence from a space to itself. And Katsura tells us how to attach a C-star algebra to this topological graph. Namely, you take this C-star correspondence of X. And I might mention that this C-star X, which I haven't quite defined it, but if you just follow the usual definition, what you get is indeed what Katsura also considers. So Katsura makes a C-star correspondence on C0 of this space G, which is the groupoid C-star algebra of this space. And then he takes the Kunz-Pimsner algebra of that. And I should maybe say that this is relative to a certain ideal. So when you make Kunz-Pimsner algebras of C-star correspondences, then you ask for some conditions, which are a bit like for a tablet C-star algebra. But one condition is more mysterious, and you can only ask for this condition on operators which act by compacts on the C-star correspondence. And Katsura found out the kind of optimal choice for the ideal on which you should ask for this condition. Okay, so that was one example. Let's turn to the next example. A discrete group is also an example of a groupoid correspondence, of an étale groupoid. And now what is a groupoid correspondence from a group to itself? So now it gets a bit more interesting. So I have here my group G acting on a set X. And I have two actions of G. And well, there are the anchor maps. Of course, for a group, the anchor map is just a point. So you might think this is not any data. But there is a condition, namely S is a local homeomorphism. So X must carry the discrete topology for this S to be a local homeomorphism. So it's just a set, not a space. And then you have a free and proper action on a discrete set. This is pretty easy. You can always choose a fundamental domain. It's again, some discrete subset. And you can use this to identify X with, well, your fundamental domain. I call it A, like alphabet. And then there is a G with, where the right action has now become simplified to the obvious action. Okay, so now the right G action is just taken care of. It looks like this. And I got this decomposition of X. Maybe I should write here homeomorphic or isomorphic. This is not equal, of course, just isomorphic to it. And now my left action, how can it look like? Well, I can say something about it, because a comma h is just a product of a comma 1 with h. And now g times a comma 1, well, I denote this by g times a and then g at a. So g times a, this is just, well, maybe I should now write down the conditions. I want that this is a left action. And this map sending g comma a to g times a, this is a g action. Or in other words, a is a g set. And then there is also this map g times a to g. And this must be a 1 cocycle. So you work out what it means for this left action to be associative. So you have something like g times h times, well, a comma k. And you can do it in 2 ways, namely like this and like this. And you compute both, and then you get something and you ask these 2 things to be equal. And this gives you a condition on this, well, this second factor, which maybe I don't write down unless you ask me to do this. You can read it in the papers. And now I've worked out what, well, a groupoid correspondence from a group to itself looks like. And if you studied self-similar groups at some point, you will see that this is a self-similarity of a group. Well, it's not quite right. It's for a self-similar group, you ask for some extra conditions. This set A should be finite. And then you also want a certain action of G on infinite words to be effective. So some action, some faithfulness condition, which you ask to rule out some kind of trivial, boring cases. The finiteness assumption actually is important for the theory. If you don't assume A to be finite, then certain things don't work so nicely. But this, well, this faithfulness condition is, well, it's just there to make the theorem more interesting, I would say. Okay, so these self-similar groups were also used by Nekrashevich to define a C-star algebra.
Ralph, could we dig in a little bit into this concept of a self-similar group?
Yes.
So I understand it is a group, say topological group with some additional structure, right?
Yes.
And is this additional structure sort of admissible? It can exist for any, say, locally compact Hausdorff topological group, or there are some obstructions, like not everything is orientable, right?
Well, the way I defined it, well, there's always a groupoid correspondence, namely the identity. So if you have a groupoid, you take its own arrow space. Well, you have left and right actions by multiplication, of course. And this is a groupoid correspondence. It's even a Morita equivalence. But this would be one of these boring cases that Nekrashevich rules out by his assumptions, I think. So he wants some kind of non-trivial self-similarity.
Okay, so there is no obstruction, but you really want something non-trivial.
Yeah.
Okay.
And of course, these groups are studied for a reason. I'm not sure whether you were, well, whether you learned mathematics in the time when fractals were very fashionable. They have some built-in self-similarity or some kind of, how is it called actually? Some small patterns repeat on larger scales, things like this. And these self-similar groups are actually useful to study such dynamical systems. So if you have a dynamical system like in the, like in this construction of Julia sets, then you can attach to this a self-similar group. This is a rather fine algebraic invariant for them. So that's why they were studied by people in dynamical systems. And Nekashevich looked into an invariant for these self-similar groups, namely, given a self-similar group, well, what you did is actually, again, you take C star X, which is now is a C star G correspondence. In this case, it's pretty easy to make it because X is just A times G as a right G set. So the corresponding Hilbert module is a free module on the set A. But then there is a left action of the group, which gives us a representation of C star G on this free module. And this is a structure again of a C star correspondence. And then again, you can make a Kunz-Pimsner algebra. And this is what Nekashevich does to make his C star algebra. Okay. In the beginning, I mentioned self-similar graphs. And that, well, I won't say much about it. Let me just say that a self-similar graph comes up when your groupoids are of the form V cross gamma. For a discrete group gamma and a gamma set V. So you take a group acting on a discrete set, and V here stands for vertices because that's actually the vertex set of this self-similar graph. And if you work out what a groupoid correspondence for this groupoid to itself is, well, you get something which is almost the definition of Excel and Pardo for a self-similar graph, except for one technical detail. Namely, Excel and Pardo start by thinking about graphs, and they want the group to act by graph automorphisms. But actually, the graph isn't the important thing. The important thing is rather this groupoid correspondence. So it turns out that for this construction to work, it's not important that the action of gamma on these sets V and E is by graph automorphisms. You need a slightly different condition, which they ask on top of being a graph automorphism action. So they have an extra condition, namely the graph automorphism action of the group gamma, which actually isn't needed at all. There's some later paper by a group of authors. I don't remember all the names. I know that Marcelo Laca was among them. They studied KMS states on these self-similar graph C-star algebras, and they noticed that everything still works if you change definition and drop one of these conditions. And so what you get is exactly what they define. And more generally, you might also just take any discrete groupoid, this transformation group, a group acting on a discrete set. This gives you a discrete groupoid. And if you took any discrete groupoid, you get pretty much the same structure. Well, it looks a bit different, of course, but the constructions you would do in the end will be almost the same. And well, then, if you follow me that far, you might not be surprised to say that if I now just take not a discrete groupoid, but any locally compact groupoid, I added topologies, what I should get is a self-similar topological graph. So this would be kind of my justification for saying that these groupoid correspondences are like self-similar topological graphs. Okay, so in all these interesting cases, there's a way of making this C-star correspondence and then take a Kunst-Pimsner algebra to make a C-star algebra out of that. Now, I have, how much time do I have, Piotr? Half an hour or a bit more?
Well, you are interrupted, so say that you have 35 minutes.
35 minutes,
yeah.
Okay. Good. So now there's two things that I should still talk about, namely going directly from this groupoid correspondence to another groupoid. So let me write something down about this in the form of some kind of commuting diagram. So we have a groupoid correspondence. So we have this X, which is a groupoid correspondence, and let's say from a groupoid G to itself. And from this, we have made a C-star correspondence. So there was a kind of a functor or something like this, which takes a groupoid correspondence and makes a C-star correspondence out of that. And then we got, well, the C-star algebra, the Kunst-Pimsner algebra. Of this C-star correspondence. And well, I should probably say that I need some properties. So in all the cases I mentioned, there is also a groupoid. Maybe I call it H, whatever. And this Kunst-Pimsner algebra is isomorphic to a groupoid C-star algebra. So what I want is a way of going directly from the groupoid correspondence to this groupoid whose C-star algebra is the Kunst-Pimsner algebra. And I see in the chat that Evgenios Kakariadis points out the authors of this paper on self-similar graphs or self-similar actions. So Larka, Rayburn, Ramage, and Whittaker did this. So I would like to explain how to go from a groupoid correspondence directly to a groupoid so that its groupoid C-star algebra is isomorphic to this Kunst-Pimsner algebra. However, there's now an issue about the adjectives on groupoid correspondences. If you think about graph C-star algebras, then well, there are some adjectives on graphs like row finite or even regular. And the graph C-star algebra is easier to study if you impose these adjectives. And in particular, the groupoid that you need to describe the graph C-star algebra is much simpler if you have a regular graph. So remember, if you have a graph and make a graph C-star algebra, then it's a groupoid C-star algebra where the object space of the groupoid involves certain paths in the graph. And for a regular graph, you need only infinite paths. But for general graphs, you have to add certain finite paths to the infinite path. And well, this is getting a bit messy. In such a situation, the solution is, of course, that you first do the simpler case and get a kind of clean construction of this groupoid H, maybe understand how to make it and so on. And then you ask a doctoral student to work out the more general case. So in the general case, my student Celso Antunes is working out this kind of groupoid model that would work nicely for any groupoid correspondence. Well,
Ralph,
actually,
but if I may interject, could you please remind us what a regular graph is?
Okay, so I suppose I need a new page for that.
Yeah.
And I might as well do it immediately in the generality that I do it for graphs first.
Yes, please do for graphs first, yes.
So for a graph, you have vertices and edges. And well, I think of it as a correspondence. So I have here the range and the source map.
Okay.
And regular means that this map R is, well, I would say it's proper and surjective. And this would probably be the right condition for topological graphs immediately. Or in other words, if it's discrete, of course, proper just means it's finite to one, and surjective means that every vertex is a range of some edge. Well, and there's two conventions, of course, for graph C-star algebras, and I always get confused by them. So it's the usual condition which you find. So there's range or source, and I want this finite to one and surjective for the map that you are used to. Okay.
So wait, Ralph, just to fix the convention, just confirm that if I take this graph and I have outgoing edge, then this is the Teplitz algebra, right?
That's I'm not good at these examples, but this is whether the direction is this or the other one. So I take this, I take the condition regular so that for every vertex I can impose the Pimsner relation, or this summation relation is something like.
Okay.
I have all the edges with a fixed range.
Okay.
And then I have these isometries SE, SE star, and that's the projection for the vertex V. I want to ask this condition for all vertices and not just for some.
Okay, so that's clear. So you just say because there's a concept of a regular vertex. A vertex is regular if it's not a sink and not an infinite emitter. So then you can impose, I mean, you should impose this second type consquirelation. Okay, so all vertices are regular. Okay, I've got you, yes.
That's the condition. And I think you mentioned the opposite convention regarding range and source.
Sure.
But that doesn't matter really.
Yeah, but exactly. But this is a good way to put it. All vertices must be regular.
Yes, then there is no possible confusion.
Exactly.
Okay, and if I have a groupoid correspondence, then this, I should write X here. Then I have my range map. I shouldn't look at this map, however. The space X doesn't even have to be a Hausdorff space. Instead, I should look at this orbit space, and there's an, I have, now both my groupoids are called G, so there is no, so I have G acting on the right and G acting on the left, and this induced range map should be proper and surjective.
So here's the opposite convention powers.
Yeah. So this would be the kind of regularity assumption if you have a general groupoid correspondence. So this map here should be proper and surjective. If we go back to the case of a self-similar group, so here my space X was this A times G. And if I take now the orbit space here on the right, I just get A. So the condition would say that A is a finite set, which is the right condition. You shouldn't ask for A times G to be finite. That doesn't make any sense, because usually your self-similar group is, the group G is infinite. Okay, so that's kind of the case when the groupoid model is nicer. So now how do you make the groupoid model? And here the idea I had is to look at actions of my groupoid correspondence. So the groupoid model and that's the groupoid H I have in mind here is defined so that H actions on spaces are in bijection. Maybe I should even say on A space V are in bijection with X actions on that same space V. And it should be a natural bijection. So a map between two spaces is equivariant for the H actions if and only if it's equivariant for the X actions. And of course, now I've just shifted my problem. I have to define what it means for this correspondence to act on a space. And why did I write V here? I think I wanted to write a Y. In my papers, I call this space Y. So now I should tell you what it means for this groupoid correspondence to act on a space Y. And then you also need to know results that a groupoid is determined uniquely by its actions on spaces in this way. So if you have two groupoids so that there's a bijection between H and K actions on a space Y, which is natural, then it follows that these groupoids are actually isomorphic. So you can define a groupoid by specifying how it acts on spaces. And I think this is also an attractive picture of groupoids. A groupoid is some kind of, well, describing, well, a class of dynamical systems, namely all its actions on all possible spaces. And so the groupoid I want is specified by saying how it should act on spaces. Okay, and what's an X action on Y now? So first of all, X is a correspondence, so there should be the groupoid G involved. So I want a G action on Y. And then I want a map from X times Y, but it's again a fiber product. The G action on Y has an anchor map, which I call R again. So there's a multiplication map. With certain properties. Now, since time is running, maybe I don't write down all these properties. So you want things like this. For instance, so here X is in X, G is in G, Y is in Y, and other properties of the same nature. You also want something like this. So in the end, I want a certain map to be a homeomorphism, so some injectivity statement. But this property here tells me that, well, I can't just conclude from this that x1 must be equal to x2. What I can say is that x1 must be, let's say, x2 times g for some g in g. And then I think y2 must be g times y1. Does that make sense? x2 g y1. I think that's exactly how it can go. G times y1. So this first relation here of associativity forces that sometimes these things are equal, and exactly then when they are. And that's the only situation when they should be equal. That's one of the conditions. And then also this map should be, well, this should be surjective, open, continuous. Okay. Conditions like this define what it means for my correspondence to act on a space Y. And then it turns out that such a groupoid model always exists and is unique up to isomorphism. And if this map here, R star, is proper, then the groupoid model turns out to be the absolute Kunz-Pimsner algebra of the C-star correspondence. And I probably should credit this theorem to Suleiman Al-Bandik. well, and maybe also in part to myself. So if X is a proper groupoid correspondence, then, well, a groupoid model exists and is unique. And the C-star algebra of this groupoid model H is isomorphic to the Kunz-Pimsner algebra of the C-star correspondence. There's one catch here. I didn't ask for this map to be surjective. So this might, maybe you wonder why I didn't do that. When I say Kunz-Pimsner algebra here, I mean the absolute one. Maybe I write here something like abs. So in this case, when X is a proper groupoid correspondence, and C star X is a proper C star correspondence, meaning that all of C star G acts by compacts. And then I can ask the Kunz-Pimsner covariance condition on the whole C star G. And this is what I call the absolute Kunz-Pimsner algebra. I ask for this condition even if this map is not injective. Well, one reason why I don't is because if I don't assume this R star to be surjective, then there is no reason why this map should be injective. But even if this R star is surjective, this representation here doesn't have to be injective. There are things like reduced groupoid C star algebras. Maybe this map factors through that for some reason because there's some kind of regular translation action going on. So in general, this map has no reason to be injective. And then, well, the way how this all works is that I get the absolute Kunz-Pimsner algebra where I ask for this covariance condition on the whole C star algebra here. Okay, and so in Suleiman-Albandic's thesis, he constructs a groupoid H with this property. He doesn't have this kind of description of his groupoid. This is something which I found later, with the goal of extending his results to cases when his theory doesn't apply. So my definition has a chance to work in cases which Albandic couldn't treat. That's the reason why I talk about this specific condition now. Okay, so this gives us a kind of a uniform way of producing groupoids that describe interesting C star algebras. So these Nekrashevich C star algebras, but also graph C star algebras, at least for regular graphs, are of this type. Now I still have some time to talk about the higher rank case, but before I turn to that, maybe I should again give you a chance to ask me some questions.
Any questions, anybody? I don't see any raised hands.
Very good. Then let's look into the higher rank cases for the remaining maybe 15 minutes or so.
Yeah.
So higher rank. I already gave a prelude to this, namely these groupoid correspondences form a bi-category. So do C star correspondences, by the way. What's a bi-category? So you have objects, which are groupoids or C star algebras. And then between these objects, you have arrows, which are groupoid correspondences or C-star correspondences. Now, in a bi-category, if you have, well, arrows which have matching sources and ranges like this, then there will be a composite arrow. And for C-star correspondences, this is this kind of very familiar tensor product construction, which is used, for instance, in KK theory or when you compose Morita equivalences. But in addition, there is more structure, namely you could have two arrows between your arrows, and that's what makes it a bi-category. So for instance, if you have two groupoid correspondences, so you have two spaces X and Y on which you have actions of the same groupoids G and H that commute and so on, then it might well happen that there is an equivariant map for both actions equivariant between these spaces X and Y. And if you have such an equivariant map, you might put it as a two arrow here. Actually, let's restrict to invertible such maps. So just equivariant isomorphism for simplicity. So you can talk about groupoid correspondences being isomorphic. And well, you might think then I can just identify them and that's fine. But there are actually good reasons not to identify them. To understand this, it might be easiest to think about C-star correspondences and some specific ones. Maybe I talk about very specific C-star correspondences and make this an example then. So let's take A as a C-star algebra. And let's say alpha is an automorphism of A. Then I can make a C-star correspondence out of it. This is just A as a right Hilbert module. With the left action, well, I use alpha and then multiply with that. So this is how we can turn actually any endomorphism into a C-star correspondence over a C-star algebra. A very familiar construction. For instance, if you now take the Coons-Simpson algebra for this automorphism, you would get the cross product for this automorphism. Now you might wonder, if you have two such automorphisms, they could be isomorphic. Maybe I call this alpha 1 and alpha 2. When are they isomorphic? Well, you need an isomorphism of right Hilbert modules, and that's the same as a unitary multiplier. So you need a unitary in the multiplier algebra. And then this automorphism should send A to U times A. This is how isomorphisms of right Hilbert modules would look like in this case. And this is an isomorphism between these two C-star correspondences if it also intertwines the left actions. So you need that alpha 2 of A times U times something is the same as U times alpha 1 of A times something. So you need this condition. Or in other words, how should I write this? Alpha 2 would be conjugation by U composed with alpha 1. So if you identify isomorphic C-star correspondences, then you will identify the inner automorphisms with trivial automorphisms. And that's not a good idea. If you studied things like twisted group actions and so on, you know that inner automorphisms are kind of more trivial than generic automorphisms, but they are not trivial. They cause co-cycles and things like that, and you have to keep track of them. And the right way of doing this is using a bi-category where you can put two arrows to tell you that certain well, automorphisms in my case are linked by an inner automorphism, but still to keep track of the inner automorphisms that you need to identify them. Okay.
Ralph, just a stupid question. In what sense U is a unitary?
This is a multiplier C-star algebra. So M of A,
okay, so the unitary in the multiplier C-star algebra. Okay.
Yes,
okay.
Exactly.
Okay, thanks.
And well, you might come to this by thinking that the multiplier algebra is the adjointable operators on A as a right Hilbert module.
Mm-hmm.
So in general, if you have two Hilbert modules, well, you need unitaries. These are the isomorphisms of Hilbert modules.
Yeah, yeah.
And here in this specific case, adjointables are just multipliers.
Yeah, yeah. Thank you so much. Yes. Mm-hmm.
Okay. So bicategories are useful because I can talk about arrows being isomorphic, like if automorphisms differ by an inner automorphism, but I can still keep track of these two arrows. Now, a diagram of groupoid correspondences. Is kind of almost by definition a homomorphism of bicategories. Now I should give this groupoid bicategory a name. Maybe I call it GR like groupoids, and the other one maybe core. So this is the C-star correspondences are called core, and the groupoid things are called GR. And a homomorphism of bicategories to GR. So maybe you're familiar with the corresponding thing in category theory. A diagram in a category is just a functor to that category. The domain of this functor gives you the shape of the diagram, could be a commuting square, could be a group action, various things. And similarly, you could look at homomorphisms of bicategories now to this bicategory of groupoid correspondences. And that's what I call a diagram of groupoid correspondences. If I do this for C-star algebras, then what I get turns out to be equivalent to a product system. More precisely, most people define product systems over monoids. So here, this would be a diagram where the shape category is a monoid. But if you, well, if you know the definition of a product system and you want to define it over a category, you probably can guess how to do that. And that's what you would get if you work out what a diagram of C-star correspondences is. And here, of course, I haven't told you what the homomorphism of bicategories is. So I have some time to do that. And I think then I probably have to finish. So for a diagram of C-star correspondences or diagram of groupoid correspondences, maybe let's take a group action. So let's take for a monoid. And this is already important. So if you want to define something like higher rank graphs, your monoid would be n to the k, the usual free commutative monoid with addition. So then this diagram consists of the following data. A monoid has only one object, so you have one groupoid. Then you have these groupoid correspondences for objects. Well, for arrows in your monoid. So for each element G in the monoid, you have a correspondence XG. And this is a correspondence on the groupoid that you specified, of course. So it goes from G to G. By the way, I view groupoid correspondence as going from right to left. because it's very convenient to have the source on the right and the range on the left. And then this just comes out like this. So, but then there is more data, because if you have now two elements of the monoid, so now you have the Groupoid correspondences xg and xh. Then, well, you would expect that there's some link between this and xgh, but these are Groupoid correspondences. Well, they can't, it doesn't make sense to ask them to be equal. Instead, you ask that there is an isomorphism between them. And this isomorphism is extra data. It's not just existence and so on. It's really piece of the data. It's part of the structure. And then there's also a condition. Namely, if you have three elements, well, you can multiply it all out. And there is two different ways of going from this to the product here by first multiplying the first two or first the last two and then the other ones. And that should be the same two arrow. So the same isomorphism of Groupoid correspondences should come out when you multiply in these different orders. This is an associativity condition. And if you would do this with C-star correspondences, then, so now you have one C-star algebra A, and you have C-star correspondences from that C-star algebra to itself for all elements in your monoid. And then you have shear multiplication maps. And that's exactly the structure of a product system for those who know what it is. Okay, and you can, well, so the notion of homomorphism of bicategories gives you exactly that kind of automatically. So that's a standard concept from bicategory theory. Now, if you have such a diagram of Groupoid correspondences, then you can go to a diagram of C-star correspondences by just mapping every groupoid to the corresponding Groupoid C-star algebra, mapping every correspondence to the thing C-star X I kind of talked about before. And then it turns out that this construction is also a homomorphism of bicategories. Yeah, just go up here. So these are two bicategories, and there is a homomorphism between them, which on objects is taking Groupoid C-star algebras, and on arrows is turning a groupoid into a C-star correspondence. And this is also a homomorphism, so it's kind of multiplicative. This wouldn't be a surprise if you have seen this Morita equivalence result. As part of the proof there, you would also show that if you compose these Morita equivalences of groupoids, then the C-star equivalence is also composed in the same way. And so this just
Ralph, we can't see. We couldn't see the bottom of the page.
Yeah, I moved up to, well, to just draw this C-star X here, but now let's go back again. Yeah. So, so there is a homomorphism from groupoid to C-star correspondences, and homomorphisms of bicategories can be composed. This is just a bit technical, but it's not surprising that you could do this. You can compose functors, and you can also compose these gadgets. And so a diagram of Groupoid correspondences gives you a diagram of C-star correspondences, which is a product system. And then from a product system, well, you can then go to a C-star algebra by taking some kind of Kunz-Pimsner algebra again. And this is how you turn a diagram of Groupoid correspondences into a C-star algebra. And if you would do this now with, well, a diagram that gives you a higher rank graph, you would get the higher rank graph C-star algebra. Here, a higher rank graph comes up if you take n to the k, and the groupoid you pick is again a discrete set. So discrete set without arrows, discrete topology. If you work out what such a diagram would give you, for this thing, it turns out to be the same as a higher ranked graph. And the higher ranked graph C-star algebra comes up in this way. And if you do self-similar higher ranked graphs, it should also work out. I think in all these cases, well, there's only one C-star algebra that you can reasonably define, and it should come out of this construction. When the monoid is like this, n to the k, then, well, you can also directly construct a groupoid out of this diagram. And it turns out that the C-star algebra of that groupoid is isomorphic to the Kunz-Pimsner algebra of this product system for a diagram of proper groupoid correspondences. That's already in Suleiman-Albandic's thesis. I haven't had time to tell you what these actions of diagrams now are. Well, it's kind of, you have a diagram with many correspondences and they all act. And then there should be some compatibility between these multiplication maps and the different actions. So it's not a magical definition, it's just the obvious one. And I think tomorrow or on Friday, you should be able to read about it because the preprint where I define this stuff is on the archive. And since my time is now probably up, I should really stop now. And well, thank you for your attention.
Thank you very much, Ralph. Yes, we raise hands. Reaction, where is it? Reaction, clapping. Okay, now let's go to questions, please. Are there any questions?
I have a question.
Go ahead, Tom.
Well, my question is about the converse to the theorem of Albandic and MEYER.
Mm-hmm.
Can you show yourself?
Yes, let me try to. It's not easy. Can you see me? Does it work?
Yes.
I can see you,
okay,
yes.
Good. So my question is about the converse to the Albandic-MEYER theorem. If you have your groupoid, can you cook up for it this for this? Can you find this H? Sorry, not H. Having H, can you construct this
X?
This X, yes. And does this construction depends on sister algebras, or this can be realized on the level of groupoid correspondences?
Well, so I have described kind of what the groupoid model is given X. Of course, this process can't be inverted. For instance, well, I think that there's many different G's and X's which might give you the same groupoid. Although I haven't really thought about a concrete example here, I wouldn't expect that this is kind of reversible in any way. And typically this H is pretty far from the original data. For instance, think about a graph, or think about the simplest kind of graph. The simplest kind of graph might be this kind of, well, just one vertex and two edges or something like this. So this would mean that your groupoid G is just the one arrow, one object groupoid, and X would be the 2-point set. So you have 2 points, this is X, and then you have 1 point, this is G. And well, there's a kind of trivial kind of action of this. So that's the kind of correspondence you start with. And then the groupoid H you produce is the groupoid whose C-star algebra is the Kunz C-star algebra O2. So that's a pretty interesting groupoid. You take this, well, the 2 points kind of are visible because you take an alphabet of 2 letters and make infinite words in these 2 letters. And then there is some kind of tail equivalence with lags on this infinite path space. But it's pretty far away from what you started with. And you need probably some intuition to see why this specific groupoid came from this data.
Okay. Is it typically the situation that this H is simpler than this groupoid G?
No, it's much more complicated. Here, G is just
so
one
this is
point.
more complicated. H is more
Yes.
complicated.
It's more like finding the hidden stuff. So in this original data here, there's a lot of stuff is hidden. At some point, in one of my papers with Suleiman, I talk about something called complete histories. So this paper is about topological correspondence, just spaces, something which happens in this example. You might think that a point in this, so if you have a topological graph, maybe let's put another page. So you have vertices and you have edges. You might think that your vertices are something like situations and edges are possible things that can happen. And a thing that can happen has some kind of initial situation where it can happen. And then afterwards, you have a different situation when something has happened. And specifying this is a bit like specifying laws of nature, which say in a certain situation, something can happen, and then you have a different situation. And then there is something like the history when you just say at time 1, I was in situation A, then something happened. At time 2, I was in situation B, and so on. So a complete history would be the series of, edges. So just a path in this graph. And so this constructing this groupoid model, the first step would be that you expand this thing to a local homeomorphism where your situations are now a complete history. So if you have such a setup, when you have situations and events, you might imagine that you can write down the complete past history, and then you can add another page. So another event, something else happens, and then you have another complete possible history. And this is now a somewhat better behaved system because now the past is determined. In this situation here, the situation doesn't have memory, so it doesn't determine the past, not the future, but you can kind of add the past by kind of taking your complete history, and then you have another system which has a much larger set of possible things. So the construction of this groupoid model has 2 steps. In the first step, you expand this kind of laws of nature description of things into a kind of a historical description when you just have a book of history and then a possible next page and so on. And then there is still this this kind of trend, this shift by, if you think of the book of things that happened, you can forget the first 5 pages. This would also be a possible history. Just a few things have been missing now. And this giving you the shift on this space. But I think I'm getting too far away from this original topic. It's a nice story, but it would be another talk. So let me just stop here.
Thank you.
Okay, so Tomek is happy. Anybody else?
May I ask a question?
Oh, go, Shao. Hello.
Hi, Half. Can you hear me?
Yes, we can hear you very well.
Okay, so so given a correspondence X between groupoid G and H, so since C star of G and H are all can be viewed as the closure of the compact function of the space, right? So it seems more natural for me to construct the core Morita equivalence. If the correspondence is a Morita equivalence, it seems more natural to construct a core Morita equivalence between the space, between a functional space. So I'm wondering here, so how we can construct in detail the C star correspondence here. So I mean C star of G, C star of X, and C star of H.
So first of all, you suggest to look at this kind of CC of X as a kind of bi-model between CCG and CCG and make a purely algebraic construction. Yes, you can do that. You want to see the formulas now for the left and right module structures and inner product, or the analysis that you need to go further?
Probably C of H is a Hilbert module, is the right one.
Yes, it's a right Hilbert module indeed. And there's an explicit formula for the inner product, which, well, you could look into the old papers on Morita Equivalence and copy and paste it. Do I know it in my hand? Well, there is a kind of heuristic behind it, which I can remember. If you have two functions, maybe phi and psi, then the idea would be that there should be something like phi star convolution with psi at G. That's how a product should look like. And what is this convolution now? Well, so there should be a phi bar. But no, I don't think I can complete this computation like this.
So maybe K and H inverse somehow here?
Well, there's something, it's some strange formula like this, and I could look into my paper, of course, and find the formula, but I better not try to do this right now. So you can find this in the paper by Antunes, Co, and me. There is just a formula, and also there is some heuristics why you take this specific formula. I think what I would probably do to derive it would be to look at the case when X is G, and then this is actually a correct formula. So then I just take the convolution of phi star. Maybe I can actually do it like this now. But this should still be phi star. So then there is no conjugation anymore. Okay. And then this phi star at this point, this would be phi of, at the moment, this is wrong. This is not the right letters. I should not choose G here. I should put G, maybe X inverse X, something like this. And now this would be phi at X, G inverse psi of X, and then there's a complex conjugation. And this formula, well, I suppose I need the source of X to be the source of G. And that should be the right formula now. It makes sense.
Yes, because it has G inverse composed with X. Yes,
exactly. So there's only X and no X inverse. This goes away in the final formula. So this middle line here is only making sense if X is a groupoid, but well, this last final result makes sense for any correspondence, and you take that formula. So that would be my kind of interpretation why this is the right formula.
I see, I see. So with the similar formula, we can construct all the C star detail of the C star correspondence and moreover the Morita equivalence between the C star algebra.
Yeah, well, actually the most difficult thing is to prove the analytic properties, like that this is now positive definite and that the left action is bounded, things like this. If you look into the original papers by Mouley, Renaud, Williams, there's a lot of stuff going into checking this kind of things.
Okay.
In the étale case, it's much easier. And in my paper, we actually check this kind of by hand. We check it by hand because we are kind of close to, but not exactly in cases previously considered. So Groupoid correspondences, well, at least for non-Hausdorff groupoids, I wouldn't know a paper where they have been really treated in this generality. But it's, well, it's not far from old stuff.
I see, I see. So I'm asking you because currently I'm studying Hopf-Groupoid, which is the function space of on the groupoid. So I'm wondering, so for me, that's why it's natural for me to construct the core product or core action structure of the Morita equivalence, which I call it the core Morita equivalence. So because we're studying the function space on everything here. So, but here I'm wondering, you construct also function space for C star structure, and also, but anyhow, we are not do the core product. We are still doing the product and action. So that's why I'm asking. Thank you very much.
Okay.
Okay, anybody else? Adam?
Maybe a stupid question. I'm familiar with the notion of a topological graph, which is as follows, that you have a set of vertices, and then between some of them, you can have an edge, but this edge is not only contain an information that there is an edge, but it also can be distinguished via homeomorphism. And I'm wondering, this notion has nothing to do with this notion which you have described, yes?
I don't think so. So a topological graph for me is what is used by Katsura. So there's a topological space of vertices and a space of edges. And then there's maps between them with some properties.
Mm-hmm. Okay, so a different story.
Yeah. And I think it's getting dark here. Probably you can't see me anymore, but...
no, I still can see you, right? No,
okay, very good.
It's also getting dark in Warsaw, as you can see.
Yes, indeed. Good. I don't see myself right now, so I'm not sure. But probably are done soon, and so I don't have to turn on the light now.
No, we are almost done. So anybody else, your last chance. This is the final boarding call for questions to RALF.
I'm taking this.
Okay, go ahead.
Okay, my question is, if you have composition of correspondences, what then happened to these groupoid models? What if you compose correspondences, then you obtain some model of the of the composition? How this can be related to groupoids for these composants?
Well, I don't think this is the right question to ask, because these groupoid models take some kind of dynamical system, and a single groupoid correspondence would be when you have a correspondence from it to itself. Now, a groupoid correspondence, if you have two of them, so you have now two groupoids and you have correspondences X and Y on them, then you might have another correspondence going from G to H. Mm-hmm. And then you might have some intertwining condition like Y composed with T is T composed with X, or more precisely, there is a chosen homeomorphism, which is part of the data actually. Mm-hmm. And if you have this data, then it will induce a correspondence between the groupoid models of X and Y. So in that sense, the groupoid model construction is also homomorphism. Hmm. So that's something you can say.
So, since this correspondences form this bicategory, I would like to see a complete bicategorical context for this groupoid model.
It's a bilimit or limit in a bicategory, if you prefer.
Oh, so this is bilimit.
Mm-hmm. It is an instance of a bilimit. The bilimit is unique up to equivalence only, which is Morita Equivalence in this bicategory. So in that sense, the bilimit concept is slightly less useful because it only determines it up to equivalence, not up to isomorphism. The groupoid model is a specific realization of the bilimit.
Okay. So considering model, groupoid model of a correspondence between two different groupoids doesn't make sense without this additional T.
Well, you have to specify the diagram. And if your diagram looks like this, you have two groupoids and a map between them. What should be the bilimit for it? Actually, it's not quite so trivial. Maybe it is just h again or something stupid like that. That would be the limit, of course. It could be that the bi limit is a bit more complicated, but I don't think it is in this example. So sometimes these bi limits are doing strange things, but I think that this diagram isn't interesting.
I have a very stupid question. Why do you call it a diagram?
Well, in category theory, a diagram is defined to be a functor from some category, a small category, into C. For instance, I could be something like we have two objects or maybe four, and you have this commuting square. If you draw a commuting square in the category C, well, that is a functor from a certain category into C, where the category has four objects.
Okay, I've got you. Yes. Yes.
And then by analogy, I could now replace C by a bicategory and a functor by a homomorphism of bicategories.
Of course, yes.
And furthermore, diagrams have limits and co-limits.
Mm-hmm.
And I didn't mention this before, but since the Tomek asked, so the Groupoid model is actually such a categorical construction. It is a limit of the diagram. And so in some sense, a diagram is the input data to construct a limit. Maybe that's the, some people might think that that's the point of diagrams, to have limits or co-limits and construct interesting things out of them. Okay.
Okay, Tomek, are you happy?
I'm happy, thank you.
All right, let me scan through everybody, no raised hands. So Ralph, thank you again. Thank you so much for your
very much.
talk. And I'll stop recording, but please don't go away.